Welcome to the next phase of our learning journey. This chapter will focus on how organizations create information systems, and it maps to chapter 11 of our book. This lecture builds on the work we've done on strategic information systems planning. That's still the context for all that we do here. And it also builds on the previous lecture on the funding of information systems. In that chapter, we thought about how organizations provide the resources necessary to support information systems function. And then we spent time thinking about how projects, information systems projects, are funded and governed, so decided upon. In this chapter, we are actually going to go deeper with respect to how the information system is actually created. How do they come to be? So we want you to appreciate how it is complex. It's a complex process to design and implement information systems in enterprises. So not for personal use, but stable, robust, secure technology that can carry an information system of a large enterprise. And to do that, organizations can either custom develop or get the technology off the shelf. So we will talk about the different approaches and different techniques that organizations implement in order to design and create information systems, enterprise class information systems that support their operations. So while I sometimes use the terms IT and IS interchangeably, it is important that you remember what you learned in chapter 2 and what an information systems is. A lot of this chapter will be about technology development. So the process of creating the IT core for an information systems or for an IT-enabled initiative. That technology can be acquired and integrated into the existing set of systems and infrastructure of the organization, or it could be custom built, designed and built from scratch, either by the organization, so that's internal development, or for the organization, that will be outsourced development. But it's very critical that throughout this chapter, you always remember that technology itself will not deliver any information processing capabilities, which is the objective of building information systems. So you have to remember, while we speak a lot about technology here, information system development then also includes the steps necessary to successfully integrate the technology with the other components or elements of the information system. Because at the end of the day, unless this integration is done, unless an information system as a whole is created and optimized, then the results expected for the initiative will not be delivered. As you remember from chapter 2, IT is not the same as IS. So as I suggested earlier, there are three main approaches to making information systems, design and development. The first one is custom design and development. Here, the organization, either internally or through partners, is creating an information system that needs to fit the unique needs of the organization. And in this process, the technology and the information systems are designed in a way that is tailor-made to the organization. Think of custom design and development as going to a tailor and having a suit being made for you. If that process works well, you don't really have to adjust to the suit or accept limitations in the suit. The suit is designed to fit you. Contrast that with system selection and acquisition. This is a situation where the technology at the heart of the information system that the organization is building is actually bought off the shelf. So is purchased from a provider that is quote unquote mass producing this technology. And so when you buy software at the individual level, for example, you buy Excel, that's a classic example of system selection and acquisition. It's not an enterprise example, of course. It's an individual level productivity software example, but it's the same idea. You are buying a software program, an application that is already complete, and it's been made to fit not you specifically, but it's designed to appeal to a mass market of users. The same happens with enterprise systems to a lower level. It's not quite mass produced, but the idea is that the technology is built for many customers. Therefore, just like buying clothes from a major retailer like Zara or Banana Republic, you know that the chances that those clothes will fit you perfectly are probably pretty small. Now, it will fit you well enough, so you will adjust to it, but it's not the same as custom tailoring. And then there's a third class of development that is very interesting, and we'll talk a little bit about it, that it's called end user development. And this is an approach that is becoming more and more common, particularly because we have more and more end users that are highly skilled and very well versed with technology. This is a situation, and again, we'll talk about it in depth, where the actual user of the software develops the software for themselves outside of the information systems function. And this, of course, like anything, has some positive aspects and some drawbacks, some limitations that we will discuss. So let's expand a little bit on the difference and the trade-offs between custom development and off-the-shelf purchasing. So the first difference is in the uniqueness of the tailoring, the customization, right? So as I mentioned earlier, custom developed software will be fitted to the specific characteristics and the specific needs of the firm that is purchasing, is having it developed. Off-the-shelf software is standardized. However, the way an organization that sells software, a vendor like Microsoft or IBM or any large vendor of software for organizations, the way that they operate is that they will customize or configure, and we'll see the difference between the two, the software for the organization. But the bulk of it is already made. It's equivalent to going and buying a pair of pants and having them slightly altered, maybe made a little shorter or a little tighter. The bulk of it is ready, and it's designed to fit lots of people in your size, but then some minor adjustments can be made. The other difference is in flexibility and control. So building software from scratch, as you realize, enables total freedoms in its design. Also, you retain control of the software over time, so it can be modified later as the organization evolves. Then the software itself can enter into a maintenance and enhancement cycle, which is typically what it's called, and be modified and extended for the new realities of the organization. This is sometimes not possible with off-the-shelf software because the vendor would have to be the one doing the adjustments. When making the case for purchasing off-the-shelf software, the proponents will say that yes, it's not completely fully customized to the realities of the organization, but buying off the shelf from a vendor can offer many advantages. Speed is one. you realize that having to design software from scratch and having it built takes time. This lag in time is not there with software that you buy off the shelf. It's already been designed and built. May have to customize it, so that will create some lag, but it's not the same as building it from scratch. The second one is what's called knowledge infusion. And software vendors will oftentimes suggest that this is the main advantage of buying off the shelf. For organizational software, enterprise type software, the vendors spend quite a bit of time trying to figure out what are the best practices, as they call them, or the processes that work best in a particular function or to solve a particular problem. Say, for example, inventory management. And the vendors spend time researching and then building those optimized processes into their code. So if you're purchasing off-the-shelf software as an organization, you're not just buying code, but you're also buying a way of performing that process. You're buying a best practice, if you will, or in theory, you're buying a best practice. And so you have some knowledge infusion when you purchase that software. Another advantage is it's typically economically attractive because instead of building, it's the same again as mass production of clothes, right? Instead of having to build a one-off, the vendor is able to spread fixed cost over a number of copies that they're then selling, so they create scales advantages and they can pass on some of the savings. And finally, particularly for mature off-the-shelf software, meaning software that has been used by organizations for quite some time, and it may be in its third, fourth, fifth iteration, right? In its not the first copy, right? Not the first try, but has been subject to feedback from the clients, modified, and gone through a number of iterations. So mature off-the-shelf products have been heavily tested, and they have been adjusted, and therefore, in theory, they should be of higher quality than something you could build from scratch. We're going to talk about each one of these approaches in turn. Let's start with custom design and development. Note that the objective of this chapter is not to make you an expert on system development. In fact, for anybody who would want to be an information systems specialist, an information systems major, you would actually take multiple courses looking at different aspects of system design and development. We are focusing on the needs of user managers. So you might be marketing, finance, operations, HR, whatever it might be. So you will be a client to the information system function, and you will be involved in system development for sure. This is a guarantee that I can make to you. But you will be involved not as a project manager or as a driver of the process, but as a participant. As such, you should be aware of what are the major approaches to building information systems and what are the trade-offs associated with each one, the pros and cons, in order to be not somebody who will be leading the project, but to be a valuable addition, a valuable partner, a valuable member of the team designing and developing the information system. So there are two main approaches that I want to discuss. The first one is, let's say, the traditional approach, still in use in many, many organizations, but this is the first attempt that was made to professionalize information system design and development. Because historically, as you know from chapter 2 and chapter 3, information system development projects were subject to high failure rates. And we defined in chapter 2 what we meant by information systems failure. In an effort to limit these failures, there were studies and efforts to professionalize the process of creating information systems. And the first attempt went under the name of the System Development Life Cycle. The major assumption behind the System Development Life Cycle is that painstaking, detailed, strong efforts early on to justify the project and plan how to complete it will reduce the risk and uncertainty in the system development. So the system development lifecycle calls for a lot of involvement early on from end user and functional managers, particularly in a phase that we will describe later called establishment of requirements. In that phase, there is a long time and a lot of analysis spent on trying to make sure that the requirements that are established from the client are precise and complete. Because once the project then starts, the goal is not to have to reevaluate these requirements and keep all of the changes of the project to a minimum. On the other side, there is the prototyping and agile methodologies, which basically were born as a reaction to the inadequacy of the system development lifecycle. And they're based on the main assumption that it's actually impossible to do what the system development lifecycle is looking for. In other words, it is impossible early on at the beginning of the project to establish and analyze and identify the requirements for the system in a way that enables then the team to lock them in and go develop. Basically, there's not enough information to do so. So prototyping and agile methods say, well, we have to take this limitation and make it into a strength. So we're going to allow for the project to be flexible and iterative, meaning we're going to allow for requirements to be revisited over time. And we're going to put the effort not so much on locking in the requirements early, but instead on leveraging tools that allow us to develop quickly and engage the customer to see the results of this development and comment on that, and use that fast cycle of iteration of requirements, building, testing, more requirements, building, testing, to refine the quality of the requirements. The two can at times be used together, particularly prototyping early on was used early in the system development lifecycle, which then proceeded with the system development lifecycle methodology. Nowadays, a lot of software is built with purely agile methods, and the system development lifecycle is no longer really considered by many organizations. However, it is important for you to be aware of both because they're both quite popular and still used, so you need to know both. Moreover, there is another advantage of understanding the system development lifecycle, which has a very established methodology. It's very clear. Once you understand it, you can understand its limitations and then use this understanding of its limitation to better appreciate agile methods. So to better appreciate the trade-off that we discussed earlier, just look at this chart. It's more illustrative than specific with respect to the numbers. But what is designed to make you appreciate is that, and you probably intuitively already understand this, is that the longer you wait to find errors or change requests. So errors are requirements that were given to you correctly, but you implemented incorrectly. and so you have to detect those errors for the system to work appropriately. And change requests are requirements that change. So the requirement as originally stated is not complete or is incorrect. It needs to be revised. In either case, you will see that as you go later in the project, so the bottom you see requirements, analysis, design, programming, testing, go live. So these are phases in the project before you can just sort of go live and use the system. It is intuitive to understand that the further down in this process you are, when you detect a change request or an error that requires you to go back and fix, the higher the proportion of the cost on the project. So system development lifecycle and prototyping and agile methods both try to minimize this. It is just the way they do it that is different. So as we said earlier when we introduced it, the system development lifecycle is an approach, a process for designing and developing information systems. As you will see, much of it is devoted to software elements of the information systems, but the latter part of the method does look at also information systems. It's a highly structured, very disciplined, formal process requiring significant planning and rigorous analysis early on, because the metaphor that is used for the system development life cycle is that of a waterfall, a cascade of activities with the objective of not coming back. So just like a waterfall in nature has water flowing from the upper levels down to the lower levels of the waterfall, and water doesn't ever really go back up. In theory, the goal with system development life cycle is to achieve the same unidirectional, not iterative process. So there's a lot of care taken in a step, in a phase, because the assumption is that once we move to the next phase, we never want to come back, just like water in a waterfall. So what are the principal phases of the system development lifecycle? The SDLC breaks system development into three major phases. Definition, which includes investigation, feasibility analysis, and system analysis. Build, which includes system design, programming, and testing. And implementation, which includes installation, operation, and maintenance. So as I said earlier, when you look at these phases, you realize it takes the centrality of software development in this approach. But nonetheless, the implementation phase is about going from technology development into information system deployment. So it does look at the full process of information system design and development, even though lots of attention is focused on the software element. So throughout the explanation of the system development lifecycle, I might use this example, which is a real project, very simple, I wouldn't say very simple project, but a simple project where the idea was to create a property management system for small hotels and bed and breakfasts. And the property management system is that software that enables a hotel to take reservations, assign rooms, etc., etc. So here what you see in this slide is all of the phases of the system development life cycle in real life on the left. And on the horizontal axis, you see a timeline in which these activities are supposed to happen. So we're going to look at each one of these major phases and then the subphases that comprise them. So we'll start with the definition phase. And the definition phase has investigation, feasibility analysis, and system analysis. So as the labels suggest, definition phase, this is the beginning of the process, and the objective is to clearly identify what the system is supposed to do, what are its features and its functionalities. And because systems like this are built for users, end users and user managers, so functional managers, need to be heavily involved in helping shape the vision for the system. The individuals, the IS professionals with which the end users are interacting during the definition phase are business and system analysts, whose main goal in this process is to justify whether it makes sense to proceed with the system, and if so, to gather the requirements. So let's look at every element of this phase. During the investigation phase, the objective is to create a vision and articulate the value proposition of the new system. So what are the goals? Why are we building it? What is the scope? What will be included in this system development effort and what will be excluded? And what are the outcomes that we expect this system to produce? This is oftentimes an informal stage where it's sort of an idea generation stage, which you probably already figured this out. It is then formalized through the business case process. In Chapter 2, we talked about business process reengineering, and you may remember that the manifesto of business process reengineering was to use the power of modern information technology to radically redesign our business processes in order to achieve dramatic improvement in their performance. So if you think about this, you apply this thought process to a business process or an activity in your organization. What you are doing is you are envisioning a new way of doing things that needs to be supported by information technology. And so what you're articulating, if you imagine this new way of doing business enabled by technology, is an underlying system that has a value proposition to deliver these dramatic improvements in performance, and it has some main goals, right? What it needs to achieve. So but this phase I won't spend too much time on, because once you understand the business case, you sort of have a very clear idea of how to perform this the investigation stage. So the next stage is the feasibility analysis stage. And this is a very important stage, because at the end of it, the project team will have to make a go or no go decision. In other words, this is a stage where you can decide to stop and not complete the project and not consider it a failure because you decided not to do it. If you take a go decision and the organization continues with the project, and you stop anywhere down the road, that would be a failure. You didn't finish the project. It's also a very important phase because you haven't spent a lot of resources at this stage building anything. You're basically envisioning and then analyzing the feasibility of a possible future project. So the investment is very limited compared to the total investment, and this is the right time to make a decision whether to go forward or not. If you remember all that we've done throughout this course, you understand information technology, you understand the role of information technology within an information system, and from Chapter 10, you understand the kind of analysis that goes into a business case, then it will not surprise you at all that there are three types of feasibility analyses that are typically performed at this stage: technical, operational, and economic. Technical feasibility looks specifically at the technology, hardware and software, and it asks the question, is it possible and viable, feasible to build the technology that we need to support the idea at the heart of this information system. So it's analysis that is purely about the technology and whether it is available and it can be built. Operational feasibility goes from IT to IS, from information technology to information system. So at this stage, you will have to assume that technology can be built. And now you're wondering or analyzing whether it is feasible to assume that once that technology is brought into your organization, the information system that needs to be built around it will actually work. So can processes be redesigned appropriately? Do we have the right people to embrace this technology? What kind of change management would be needed, and is it going to be successful? These are obviously very difficult questions to answer because you're looking into the future, but that's why you have to do the analysis. And the latter one is an economic feasibility that looks at specifically at the financial viability of the system. And if you remember from chapter 10, we did this in the business case with financial metrics. With this analysis completed, and again, the objective, as you recall, of this type of analysis is not to eliminate uncertainty, which is impossible, but to reduce uncertainty, then the project team should be able to propose a go-no-go decision. Through the process of budgeting, then these recommendations are sent forward for many reasons that go beyond just the specific projects. The project will be funded or not. If it is funded, then the design and build begin, and it becomes more and more costly to turn back the more we go forward. So if you ever are involved more on the information system side of the equation with a system design and build, most likely your role will be as a business analyst or a system analyst. If you are involved as an end user, you will be interviewed through a process of requirement elicitation. So what happens at the system analysis stage? This is a central, fundamental stage. And it is at this stage that the interaction between information system professionals, typically system analysts, and end user and functional managers, so the client of this building project, if you will, there's a lot of iterative interaction between these individuals with the objective of surfacing with as much precision as possible all of the system requirements. So what is the system supposed to do? What are the inputs that the system will accept? What are the outputs that the system will produce? What do they look like in terms of user interface? So scenario analysis like the ones you see on the right here will have to be produced. So for example, this is a reservation taking process for the property management system that I was suggesting earlier. And this is a flow chart that tries to imagine what are all of the possible things that will happen during this reservation process, and therefore what are all of the possible support functionalities that the system needs to have to support and enable this process. So it can be depending on the complexity of the system, this could be a very lengthy phase with a lot of back and forth. The objective is at the end to get to a point where the requirements are established in a requirements document and the client signs off on them, meaning reads them and says, yes, this is exactly what I would like. At this point, the requirements are frozen, and in theory, this doesn't really happen in practice, but in theory, you would want, once the requirements are frozen, to never have to go back to the users to change the requirement or try to understand better the requirements, and just simply move into the build phase. You recognize that unless the systems are very, very simple, or the rebuilding with new technology of existing systems where it is very clear already what the functionalities of the systems are, unless you have these very specific cases where the requirements are pretty clear, then if you're building new systems, what happens often is that even the users don't know exactly what they want. And so a lot is lost, quote unquote, in translation between the clients, the business side, and the designers. And so the system analyst is a central figure. Great system analysts are able to elicit requirements with more precision, asking the right questions, and make sure that the amount of going back after the requirements are frozen is actually minimized. Here with our running example of the reservation process, you see how precise you have to try to be with the elicitation of the requirements, right? So the reservation functions are to clear all the fields with a reset button. That's a requirement for a functionality. Be able to retrieve a guest profile information from the guest database and maybe pre-populate the fields if it's a returning customer. So this is the level. Imagine it this way. Every button, every input field, every piece of data that populates the system needs to have a complete specifications of all the requirements associated with it. It's a lengthy and sometimes exhausting process, but in the system development lifecycle, this is necessary, because remember, the system development lifecycle assumes, as its basic assumption, that we want to do all the work up front to get the requirements and not have to then come back later because it's costly and revisit and change these requirements. System analysis completes the definition phase. So you have investigated the system, which means imagined a new way of doing things, analyzed the potential of this system, figured out if it's technically viable, operationally viable, and economically viable. And then once you decided to go for it, then you spent considerable time analyzing and specifying exactly what the system will do, how it will do it, with what inputs and what outputs. Now, with that phase complete, it's time to actually build the system. And so there are three stages here: a system design stage, a programming stage, which is probably what everybody who doesn't understand system design and building think that software creation is all about, right? Just programming. So system design, programming, and then testing. Let's look at each one one at a time. So the system design stage is another fundamental stage. It's more technical. In fact, architects are involved. And if you remember from chapter 1, architects are very technical individuals with a lot of experience that have to make architectural decisions. So very high-level decisions about what technologies will be used, what are the general frameworks for system building. So based on the system requirements, once it's clear what the system needs to do, the architectural design is created. So the outcome of this is a precise set of documents that are now much more technical and actionable by system developers, programmers. These documents that translated the user level system requirements into architectural design choices and design building documents get fed into the programming stage. And like I said before, if you ask any of your friends who doesn't know anything, what is system analysis and design, they'll probably think of programming. Programming is really just the process of translating the abstract design into a set of instructions that can be executed by hardware. So as you know from the chapter on software, there are two elements to this: algorithm design and coding. So in this phase, that's what the developers or programmers will do. They will also do something that typically programmers don't like to do, which is document the software. Documentation is, of course, essential for system maintenance in the future. It's essential for upgrading the software later. It's essential when new people are brought in on the project and they need to understand existing code to contribute to it. And then the final stage in the build phase is testing. And testing, of course, happens throughout. Every time that a developer produces a piece of code, they test it to see if it works. But what we're talking about here is more formalized, comprehensive testing of the complete application. This is what happens at the testing stage. And interestingly, there is a economic feasibility analysis also implicit in the testing phase. The objective is never to really achieve perfect software and release it and wait to release it until it's perfect, right? The objective is to release it when it's good enough. And here, good enough means that spending any more time on refining the software has a cost in terms of time that is not justifiable. So what happens normally is that software will be released, will be version 1, and then there will be known bugs, known limitations, as well as users start to use it, new errors or bugs or flaws and limitations will surface. They will go into a queue for the maintenance, right? They will go into a queue and they will get prioritized, the most important first, and then patches will be offered, so code that goes to resolve some of these errors. And over time, new releases, right? So version 1.0 will have some bugs that will be cleared up in version 2.0. And you see this all the time when your iPhone or your Android device updates some apps. It'll tell you what the app's new functionalities are, and oftentimes there will be a standard phrase called bug fixes and enhancements, right? That's what we're talking about here. So the outcome of the build phase, so what we have as this stage is a releasable software program. So we are done with the IT part of the information system build and implementation. And in fact, implementation is the last phase. It consists of installations, operations, and maintenance. The first stage in implementation phase is installation. So installation occurs very practically when the software goes live in production. So up until this stage, the software has been in development servers. So it's been on the infrastructure of the IS function, whether internal and external, and it's on development servers. It's been tested on development servers, but the users haven't really started using it in what's called production. So installation is when the software moves from development to the production hardware. Databases are populated with the data, with real data, and the organization starts to use the new system. This is a phase that it can be highly disruptive, and so typically occurs during slow periods of the organization. If you are a company that makes software for taxes, you don't want to release it in June when everybody's doing their taxes, right? And also the way the installation is done is can be different, and different approaches will be best in different situations. The approaches to the implementation stage are parallel, direct, phased, and pilot. So you could have a phased, parallel installation where you have the old system and the new system being both operational for a period of time. So they run in parallel. That's why it's called parallel. This is, of course, advantageous when you can do it, because if at any moment in time there's something that goes horribly wrong with the new system, you still can maintain the old system. Of course, it's costly because you are duplicating effort, or you're doing everything in the old system and the new system. And in some cases, it's just not possible, particularly when you have a specific deadline for which the new system needs to be operational, and you're up against the deadline, then parallel might not work. Direct cutover or direct installation is a situation where you are doing stopping one system and starting a new one immediately. So this is a situation where, for example, you cannot run in parallel. Typically this type of cut over happens over weekends or over at night. And it's sort of an abrupt change from one system to the other. Another approach is called the phased approach. And what this little image is trying to show you is how components of the system are turned on at different times. It's similar to parallel, except that you're not running the whole system in parallel. You're just turning on components. This is typical for large software programs like an ERP that is modular, has multiple different elements that are interrelated but somewhat independent. For example, an ERP will have a financial module, will have a order inventory module, will have a production module to run the factory. And so when the system is built this way, then phased approach becomes viable. And of course, it reduces the risk associated with a direct cutover, the previous example. And then the last way to do this, which is called the pilot. And this is viable when the same system needs to be installed in multiple different units. So a perfect example will be a restaurant chain. And say you have a reservation management system or a table management system. In this kind of scenario, you may have 50 restaurants. And so you have the luxury of trying the implementation first in one unit, then in another unit, and you can kind of see what the problems may be and work out solutions before you go to all the units. And so the way you decide which units to pilot on is also interesting. You may choose a really high-performing unit to ensure that there are no major problems. Then you could look at a low-performing unit, one where you expect to see the most problems, just so that you can preview how to fix them. And then once you have this sort of information about what happens during installation, you can roll out confidently to all the other units. So what we've talked about so far is the technical side of the implementation phase, right? Where we are installing software on production hardware. But there is obviously the social side of the implementation phase, which is really where you go from technology to IS. So the elements here are typically training, right? End user training will occur during installation. Generally is informal settings like a classroom. Increasingly is virtual. In some situation, you have to imagine that training is not a possibility. This is typical with customer-facing apps, particularly simple apps like Instagram that people just download for their use. They have no real reason to use them other than enjoyment. And therefore, you have to realize, we talked about this before, you have to realize that when this happens, the way the software is structured has to allow for the lack of end user training. So the way typically designers will do it is that they'll try to keep the app usable with very few simple elements to it, commands or buttons, and so you can get much of the work done, and then let the other ones, the more complex elements of the application, be discoverable over time, so that the more people get engaged with the app, the more they can then do the work to train themselves, in essence. The other big elements, and we've known this from the very beginning of this course, particularly when we talked about chapter 2, is that anytime that there is a new technology disruption in an information system, you have systemic effects that need to be managed. The systemic effects are managed through a process called change management, which is the process of smoothing out transition from the old way of doing things to the new way of doing things, handling user resistance, inertia, incentives, making sure that incentives are aligned. There are no negative or counter incentives at play. And of course, as you remember from chapter 2, the degree to which there is change management effort needed, which as a person involved in the project, you should be used to anticipate. But the amount of change management that is needed will depend on the magnitude of the organizational change that the system brings about. If it's simple automate change, will be lower than if it is informate change, than if it is transfer level change. And we talked about this in chapter 2. So once installation has occurred, the last two stages in the implementation phase are operation and maintenance. So the operation stage is sometimes called the infusion stage. Is that stage at which the system becomes part of the organizational work system, the way of working for the organization. It becomes a permanent asset of the organization, and it becomes infused in the way we operate in the firm. Then at this stage, we come back into the cycle. So it's called the system development life cycle because you have to think of it as a continuous cyclical process. There's this waterfall through design and build and implementation. And then at the end, you are basically re-entering the cycle through the maintenance stage. So you have to imagine now that the organization is working with the system, and some things are going well, some things may not be going well, bugs are identified, enhancements, things that could be done better are identified, new requirements may be identified. So all of these feedbacks flow back to the system development team, who will need to start prioritizing them. And some of them may be required to be patched right away, like security flaws that need to be eliminated right away will be highly prioritized. Others will sort of go into a queue and be designed into a major iteration or a major new version. One thing that people don't think about that you need to be aware of and it's represented by this simple picture on the right. But you'll remember that we said from the very beginning that organizations are unique and are also not static. Organizations evolve over time. So at Go Live, the needs of the organization and the performance of the system should be the same, right? So you see the two lines are overlapping. So what that represents is that if we built the right system in the right way for the needs of for the requirements that we had received from the users who had articulated these requirements correctly, and I recognize these are a lot of ifs, but if we assume that all that happened, then the system that we build is exactly what the organization needed. However, if the organization is dynamic, the needs of the organization will change. So the performance requirements will start to diverge from the performance actually delivered by the system. And so there will be enhancements and new versions that try to catch up. But oftentimes what you will see is this divergence between the two. And imagine getting a job in this company kind of middle of the way. You might have the typical reaction of, who's the idiot that built this system? This system does not do what we need. Yes, before you become a naive user just complaining, you have to first ask yourself the question, when was this system first designed and rolled out? If it was, as in many systems, rolled out in the 70s or 80s, well, then you should expect a divergence. And so what happens is that when this divergence is no longer tenable, or it's leading to performance limitations that are considered too big, or if the organization is forward-looking and wants to anticipate these limitations and preempt them, then that's when you will have the scrapping of the system and the building of a new system for the new performance requirements. While prototyping and agile methods come in many forms, have different names, the objective here is not to become an expert. So I will treat them all as one and just really spend time helping you with the intuition. What's new about them? Why were they developed? And what are the advantages and limitations of these approaches, without trying to separate them or have you memorize different approaches to Agile, Scrum, and other archaic names that you can always learn later if you have to. We said this at the very beginning. Prototyping is kind of a reaction to the system development lifecycle, and it basically challenged the number one assumption of the system development lifecycle, which is that it's possible to clearly estimate budget, time, and requirements for a complex information system project. Prototyping an agile approach basically says that's just not possible. So instead of fighting this difficulty, let's embrace it. Let's create flexibility in the process. And it is this flexibility in the process enabled by tools and techniques to rapidly iterate in the design and build that will allow us actually to get a lot more user input during many more phases of the design. As the software becomes more and more complete and complex, we can iterate with these requirements, and therefore in the end build something that is much closer to what
doing so would enable us to avoid the scenario in this cartoon. And if you stop the video and take time to read it, it's even quite funny, but it shows how very easily a project of the difficulty of an information systems project can get sidetracked, where the customer wanted something relatively simple, and then different players, from the consultants to the programmers to how the customer themselves explained it, created all kinds of different results. While in the end, what we wanted, we could have converged rather quickly with an iterative process. An iterative process that traditionally would be called prototyping. Today, it really goes under the name of agile methods. As I said earlier, it's not the objective of this class to become an expert on all kinds of agile methods and terminology and the history of prototyping or what have you. In fact, typically in an information systems program, there is at least one class, the project management class, where these topics are covered in depth. There's often a capstone, a system analysis and design course where these concepts are practiced. So at this stage, we just want to be familiar with the intuition. And the best way to see that is to understand the Scrum framework. And instead of sitting here and explaining it, I have a video that does a really good job at explaining it. So I will play that for you.
Introduction to Scrum, a 7-minute training video with details on what you need to start using Scrum today. This video is intended for people who are just getting started with the Scrum framework and need a quick primer. Hi, my name is Steve Stedman, and I am the founder of Utility Software. In this video, we will cover the basics behind Scrum, and we'll take a look at how Scrum compares to waterfall development, and we'll examine the 3 roles, 3 artifacts, and 3 ceremonies that make up Scrum. First, let's take a look at how Scrum compares to the older alternative of waterfall development. Waterfall typically goes through a lengthy planning process, which could take several months, followed by building the product, which again could take many months, and then testing the product, reviewing, and eventually deploying the product. At this point, you may end up bringing the wrong product to market if market demand or technology has changed since the original plan was developed. There are several problems with this method. First of all, the planning must be completed before any work begins, and in most cases the planning is done without entirely understanding the project. Once development is being done, oftentimes things get sent back to the planning phase, and the project either needs to start over or the developers are just criticized for not understanding the plan. This cycle can happen many times. When development is done building the product, it gets thrown over the fence to test, where when problems are encountered, it bounces back to development and sometimes back to planning. The same issues occur in the next few steps, with lots of backstepping and doing over. This can lead to lag times and many months to several years in order to get a product out the door. With Scrum, an implementation of Agile, the process is broken up into smaller pieces. First, we do just enough planning to get started with, building the minimal feature set. We build what was planned. Next, we test and review that small feature set and get it ready to ship. When that cycle is complete, we end up with a potentially shippable product. This process usually occurs in a time period of 1 to 3 weeks. This is then repeated time and time again, reducing the time from planning to development to testing. Each time through the planning process, we're doing just enough planning to complete the next incremental release. You end up with several incremental releases called sprints. A sprint usually takes from 1 to 3 weeks, and you just keep repeating these sprints until your product is feature complete. Sometimes you may end up shipping your product after the second sprint, or the third, or the fourth, or even further, but you eventually end up with a shipping product. In Scrum, there are 3 key roles that are needed for the framework to work well. First, the product owner. This is the person responsible for defining the features that are needed in the product. The product owner has the bright ideas that turn into products. The Scrum Master is a servant leader to the team, responsible for protecting the team and the process, running the meetings, and keeping things going. The team can be made up of developers, testers, writers, and anyone else that helps in building the product. Team members often play multiple roles. Some days developers may end up doing test, or testers may end up writing. Either way, the team works to get the product done. There are 3 artifacts or documents that are used in Scrum. First, the product backlog. This is where product owners create a prioritized list of features known as user stories that could go into the product. This list evolves and changes priority with every sprint. User stories are a way of describing a feature set that follows the as a user, I need something so that reason format. This way of phrasing a user story allows the product owner to specify the right amount of detail for the team to estimate the size of the task. The highest priority user stories go into the sprint backlog. These get estimated for size and are committed to for the next sprint. Burn-down charts show the progress during a sprint on the completion of tasks in the sprint backlog. This chart should approach 0 points as the work is being completed. There are 3 ceremonies that make up Scrum. Think of these as meetings or discussions. Sprint planning is where the product owner, Scrum Master, and team meet to discuss the user stories and estimate their relative sizes. The daily Scrum is a brief stand-up meeting where the team discusses what they have completed since the previous meeting, what they're working on, and anything that might be blocked or need help. The sprint review and retrospective occurs at the end of the sprint. This is where the team demonstrates the completed work to the product owner, and then the team discusses what they can do to improve the process going forward. Let's bring it all together and take a look at the Scrum workflow. Start with the product backlog, which is where the product owner builds a list of the bright ideas and features that could go into the product. The product owner prioritizes the list and brings the top items to the team. Sprint planning is where the team, product owner, and Scrum Master discuss the top priority user stories, determining what can go into the next sprint. The output from the sprint planning meeting is the sprint backlog. This is a list of user stories that have been committed to for the next sprint. The entire team and product owner have a solid understanding of what each of the user stories involves based on the discussions from the sprint planning meetings. The sprint is a 1 to 3 week time box where the work committed to in the sprint backlog is worked on through to completion. During the sprint, the daily Scrum occurs as a stand-up meeting where the team discusses what they have completed and what they are working on, as well as any blocked items. The outcome of the sprint is a potentially shippable product. Potentially shippable means that the product owner can decide if it is ready to ship or if there are any additional features needed before it ships. At the end of the sprint, a sprint review and sprint retrospective meeting occurs. The sprint review is where the team showcases their work to the product owner, and the retrospective is where the team works on what they can do to improve their process. Repeat this workflow for each sprint.
As you remember from our coverage of the system development life cycle, at the end of development we enter sort of a maintenance and operations cycle. And so in reality, in organizations, we have working systems that are constantly being worked on. Think of an application that is customer facing, like a pizza ordering app. And at the same time, of course, it is maintained and operated. Traditionally, these two functions were separate. The development team completely separate from the operations team. And this created challenges. I have a video that explains very clearly what those challenges were, and I will play it in a minute. But the solution that has been introduced in the last sort of decade is the idea that we have now the tools and the techniques to increase coordination between development and operations, such that we could actually create DevOps teams that actually do both at the same time. And these teams are able to leverage automation tools that streamline a lot of the elements of the testing and production process, such that the two tasks of development and operation can be tightly linked. And again, the video will explain exactly what's happening. One thing that I would say is that this approach has been so successful that we now speak of DevSecOps because of the rising importance of cybersecurity and how cybersecurity needs to be thought of as an important element of development and of operations. Then this idea of DevOps, of coordination between development and operation, has been expanded to also include information system security or cybersecurity.
Right from the start, software development comprised two different departments. The development team that develops the plan, designs, and builds the system from scratch, and the operation team for testing and implementation of whatever is developed. The operations team gave the development team feedback on any bugs that needed fixing and any rework required. Invariably, the development team would be idle awaiting feedback from the operations team. This undoubtedly extended timelines and delayed the entire software development cycle. There would be instances where the development team moves on to the next project, while the operations team continues to provide feedback for the previous code. This meant weeks or even months for the project to be closed and final code to be developed. Now, what if the two departments came together and worked in collaboration with each other? What if the wall of confusion was broken? And this is called the DevOps approach. The DevOps symbol resembles an infinity sign, suggesting that it is a continuous process of improving efficiency and constant activity. The DevOps approach makes companies adapt faster to updates and development changes. The teams can now deliver quickly, and the deployments are more consistent and smooth. Though there may be communication challenges, DevOps manages a streamlined flow between the teams and makes the software development process successful. The DevOps culture is implemented in several phases with the help of several tools. Let's have a look at these phases. The first phase is the planning phase, where the development team puts down a plan, keeping in mind the application objectives that are to be delivered to the customer. Once the plan is made, the coding begins. The development team works on the same code, and different versions of the code are stored into a repository with the help of tools like Git and merged when required. This process is called version control. The code is then made executable with tools like Maven and Gradle in the build stage. After the code is successfully built, it is then tested for any bugs or errors. The most popular tool for automation testing is Selenium. Once the code has passed several manual and automated tests, we can say that it is ready for deployment and is sent to the operations team. The operations team now deploys the code to the working environment. The most prominent tools used to automate these phases are Ansible, Docker, and Kubernetes. After the deployment, the product is continuously monitored, and Nagios is one of the top tools used to automate this phase. The feedback received after this phase is sent back to the planning phase, and this is what forms the core of the DevOps lifecycle, that is, the integration phase. Jenkins is the tool that sends the code for building and testing. If the code passes the test, it is sent for deployment, and this is referred to as continuous integration.
Irrespective of the approach that is followed, whether it's the system development lifecycle or is it prototyping and agile, the location of development could be internal or external. So the way I've presented the two approaches so far is implicitly to say the information system professionals in the organization are doing the custom development. But it could very well be that those that are doing the project are not member of your organization, but they are external provider. That's the case in outsourcing. You already understand the concept of outsourcing from chapter 10, so we will not spend so much time on this. You have to think of it as a classic example of outsourcing. So an external service provider is doing something of value, but in this case, what that something of value is helping the organization with custom design, software design, and building. And with the advent of the internet and offshoring, the ability to move some of this outsourcing to other countries, then there's a trend where the development teams are now virtual. They work together, but they're not physically located together. And because software is knowledge work that doesn't require physical production of goods, then it's very amenable to a virtual development. Whether in an outsourcing scenario or internally, so far we have only talked about situations where custom software is being written, right? So custom development of systems is what's happening. But as we know from the introduction, there is a whole different way to provision software, which is buying it off the shelf from a vendor. So what we're going to describe now is the system selection process. And particularly early on in your career, I would suspect that if you are in marketing, finance, or any other functional area, you will be very likely to be involved in a system selection team. So I'll describe the process by which system selection occurs, and you will see is a derivation of the system development lifecycle. So understanding the system development lifecycle, even though it's kind of an old approach, becomes the basis for understanding a lot of processes that are currently in existence. So the system selection process is the process of identifying, acquiring, purchasing, and then implementing off-the-shelf software from vendors. And it's typically a process that is supported by the information system function, but it's typically driven by a functional area. So that's why I was saying if you're not going to be an information system professional, you're still much more likely to be involved in this type of process. The phases are described on the right on the image, and as you can see, it is very similar to the system development lifecycle. So you have a definition phase, and this one is going to be somewhat different. You're going to have different activities that you perform, so we'll look at those. After that, build, similar, and implementation, exactly the same as the system development lifecycle. So let's look at each one in turn. We will have an investigation stage and a feasibility analysis stage that are very similar to the ones that we have in the system development lifecycle. So we're still in the investigations, try to figure out what are the goals and scope of the design, and then through feasibility, trying to understand, is this technically viable? Will it work? Operationally viable? Will it work if the technology works? Will it work in our organization? And economically feasible? Will it work from a financial standpoint? So no major differences here. This is where we start to diverge a little bit. So we have a system analysis stage similar to the system development lifecycle, but the focus here is on determining specific functionalities that need to exist, will not be developed. Kind of a checklist of functionalities that we need. This checklist of functionalities gets then evaluated, so we have to formulate some specific evaluation criteria. And typically, an organization will identify essential features, things that we must have to consider a software. So we look at a software from a vendor through a request for proposal, and if it doesn't have any of the even one of the essential features, then we cannot consider it. Then there's value-adding features which are non-essential, but we'd be willing to pay a premium for. So they will not disqualify a vendor from being considered, but rather they will make that vendor more appealing to us. And then there's a bunch of non-essential features that would be nice to have, but we may not even be willing to pay for. Extras, if you will. So at this point, with the requirements in place and the evaluation criteria in place, you can search for literature or information about the vendors and compile a short list of vendors that you are going to send the proposal to. Here's a key thing that you have to consider. You want a request for proposal to be structured by you. In other words, you shouldn't just go out to vendors and have them pitch you software for your problem, but you should actually give them a template of exactly what you will evaluate and how you want them to respond. This is important because it will make the comparison between the different responses very, very simple, or simpler, I should say. Once you have compiled the RFP, then you distribute it, and you will want then the responding vendors to identify, according to the levels of the evaluation, the requirements, the features of their software. So interested firms will respond to the RFP, and you'd have to create an internal selection committee that will evaluate the requirements according to the evaluation criteria. Vendors are then ranked, right? So you have an evaluation stage where the alternatives are evaluated according to the criteria that were established before, and there'll be sort of a list of top vendors with whom you then go to negotiate, draft and sign the contracts, try to focus on total cost of ownership, but it's sort of like any buy decision for a complex product. Once the RFP is made, then you enter a negotiation with the vendor. So with the definition phase complete, we enter the build phase. The steps are similar: system design, programming, and testing, but they actually are conceptually similar, but they're going to be different because the bulk of the system is already built. It's already been evaluated. So during system design, the system design stage, what's really happening is that the software is being configured. So complex enterprise level software, as you know from chapter 3, will come with a number of possible configurations based on the idea that every organization is unique. So everybody's buying standardized software from a vendor, but still it will need to be adjusted to the specific of the organization. So there are parameters built into these complex softwares that can be configured when a particular contract is written between a specific organization and the vendor. There are also situations where programming might be needed. So if configuration is not enough, then there will be customization of the software. And this will be the process of actually modifying the application or adding components to it, so-called bolt-on components, for example, for ERPs, as you know from chapter 3. But if there are very specific needs of an organization, typically negotiated during the negotiation process, the vendor will be willing to custom build some elements or modules or extra features for the client. So that part will require programming. And then finally, there's a testing stage, but the testing isn't the same time of testing typically done on custom software, because that testing has already been done for bugs and etc. But it will be testing to evaluate system performance in the organization, specific scenarios, rather than just looking for bugs. And so the last phase is the implementation phase, very similar to the system development lifecycle. There'll be an installation, operation, and maintenance. The big difference here is that this is where all the advantages you had up front in the definition phase and the speed with which you could acquire versus build are now balanced by some of the disadvantages. So the degree of process change and of organizational change and adjustment to the technology that is required for off-the-shelf software is typically typically much larger, right? Because the software wasn't custom built for the organization according to system requirements expressed by our users. The system was just selected among a list, and it was the one that it was closest to what we want as an organization, but again, probably not as close as something that would be specifically tailor-made for us. So training may be more involved. Definitely change management will be more substantial. And so when you think of implementation for a system selection process, you need to plan for more involved work. In fact, there are specialist organizations like Accenture, IBM, often called integrators, which are partners to large off-the-shelf vendors like Oracle or SAP, for example, for enterprise systems. And these integrators are specialists in the implementation phase of that particular software from that particular vendor. So when you negotiate with SAP, it's typically a three-way negotiation between your organization, the vendor, SAP, and one of the integrators, just as a testament to the fact that the implementation process is so much more involved. The last approach that we need to talk about is goes generally under the name of end user development, and it's while custom development and system selections are sort of two approaches to do the same thing, to acquire and implement enterprise level software for an organizational function or the whole organization. End user development is different. It's at a different level. So let's talk about this for completeness. So end user development is a general term that captures a lot of different specific things, but they generally have to do with knowledge workers, not information technology professionals. This is the key. End user development is the creation of software by individuals who have talent, skills, but they're not information system professionals and do not work for the IT function. Examples are any spreadsheet models written by a marketing analyst, or any database, small personal database written by a sales executive to keep track of their contacts. And more generally, any software program built with and kind of user-friendly third-generation languages like R or Python that a user is building for themselves. And so, interestingly enough, many of you know Python, or at least been exposed to it, and many of you have been exposed to database development. So you'd be a prime example of somebody who will engage in end-user development. So imagine a situation that you become an analyst in the HR function and you're doing some data analysis for HR. You might actually write your own R script or Python programs to systematize your work and maybe to be more efficient in doing reports that you do on a regular basis. That's a perfect example of end user development. Why would you do that? What are the benefits? Well, first of all, increase speed. If you are writing the application for yourself, if you're writing the software for yourself, you don't have to put in a request to the information system function. It doesn't have to go through an approval process and maybe be denied. And even if it's accepted, you then don't have to rely on somebody else, some developer, to give you time out of their busy schedule to do the project. Also, in general, you may be more satisfied because you're able to craft a program and an application that is very close to what you exactly want. Right? If you're writing your own software programs, you have a clear vision of what you want. You don't have to explain it to somebody else. Now, these tend to be relatively simple because the level of skill that somebody would have as an end user is limited. And working in partnership with an IS professional, they might actually make suggestions to make the software better. But you wouldn't know that, and so tend to be more satisfied. Another advantage is for the IS function, the end user development actually reduces pressure on them because they don't have yet another request for a report or an analysis to be done, because you're going to do it on your own. So what is the other side of the coin, right? If we've learned one thing in this lecture, is that for every approach there are benefits and limitations. So what are the risks of end user development? First of all, in general, end user development has an incredibly varied level of quality in the software that is built. Some end users are very talented, very thorough, very precise, and they may actually develop good quality software. But a lot of the end users who engage in development are not trained in system development. So they will not document their software, most likely. They very rarely know how to systematically test an application. So the level of quality is going to be extremely varied and generally unreliable. Also, typically end users have a day job. They're not software developer. So they're developing this software to become more efficient in their actual day job. And so rapid development is always a driver of end user development, right? You want to get the software done quickly so that you can use it to do your job. And so the likelihood of having errors embedded in the software, along with the limited testing that typically end user developers do, brings a high incidence of errors. There are studies done on the incidence of errors in spreadsheets used in organizations, and the errors tend to be high. And the last one is what's called continuity risk. Because end user developers rarely will apply a professional system development approach, they will generally not test and typically not document their work. They tend to be the only one who can maintain the software that they built. So once they move on to maybe a different job or in a different organization, their software rarely gets used by whoever comes next or whoever is left. So it doesn't have any continuity for the organization. So this concludes our lecture on software creation. This can be a bit of a dry and boring lecture, but it's nonetheless important that you have kind of an overview of the way in which organizational enterprise level systems are designed and built, because you will be involved in such processes, and understanding the overall picture will make you a better asset on that on those teams that you'll be part of.